Okay. Hello, everyone. Welcome to Percona Live. In this session, we'll be talking about how we solved the complex problem of scaling an application at LinkedIn, which uses MySQL as a backend data store using Vitess. My name is Apoorv Purohit. I am a site reliability engineer at LinkedIn, specializing in MySQL. I started my career as an application developer in 2016, working on C++, Java, and MySQL, where MySQL caught the most of my interest, and that motivated me to become a database engineer in my next career move. I worked 2 years as a full-time MySQL DBA before joining LinkedIn in 2019 as an SRE.
Hey, I'm Karthik Appigatla. I've been working on MySQL for more than a decade. I started my career with Yahoo and then moved to a company called Python, and then I worked for Percona as well. And then I joined LinkedIn, and it's been 5 years I have been at LinkedIn. I authored a MySQL 8 cookbook. You can check it out at Amazon. And you can connect to me on LinkedIn at linkedin.com/in/Appigatla. And Apoorv will be taking over this session, and he'll present on how we used Vitess at LinkedIn and what is the data from a normal standalone instance to Vitess, and what are the challenges that we faced, and how we overcame the challenges, and finally what is a future roadmap of Vitess at LinkedIn. So thank you.
Yeah, thanks, Karthik. Thanks a lot. Please feel free to put your questions in the Q&A section. All right. So before diving into the session, let me try to make things a little relatable for the audience. So here are a few challenges that you might be facing or might have faced in your application that uses MySQL as one of the major backend data store. Number one, the application is write intensive. The writes are obviously more than the reads, and a lot of transactions are running on the MySQL primary host, making the CPU load go higher, and the apps start to experience some latency. Number two, it's a very critical application, so a downtime will mean an outage, and the users will be affected big time. So the application cannot afford a huge downtime. Number three, because it is write intensive, the data is growing at a very, very fast pace, and we are talking about adding more than 1 million records every day. And lastly, the backend data store is MySQL, of course. This is an important point, where the application relies on MySQL for its ACID compliance and ease of use, and does not prefer to move away from MySQL. Sounds a little bit relatable, right? Sometime or the other, we all have been there, and those who haven't been there have definitely heard of such problems. So let's talk about our application as well. So it happens in any infrastructure that deploying a bad code brings the colo down at times, pushing a corrupted config blocks relevant traffic, or maybe an outage in an app results in outages in multiple apps. So tying all these events together and correlating them makes it easier for anyone to debug the issue quicker and increase the overall reliability. So there is such a tool at LinkedIn which does that actually connects to every component in the infrastructure and provides insights about every operational event. So when I say operational event, it means any activity which is performed in infra, like a cluster by adding a node, deploying an application on a host, reclaiming unused hosts, to the spare pool, switch maintenances, etc. So we call this tool informed. It has APIs to collect the data real time about all such events. So just imagine the size of data when I'm talking about operational events and the amount of data it generates and then consumed by the APIs. It also has read APIs to power its UI, which provides in-depth visualization to debug, deep dive, and correlate issues. Elasticsearch, as you can see, is used as a primary search data store. And all the event mutations are pushed in Kafka, which can then be subscribed to and consumed internally as well as externally. There is also a subscribe API that has been built, used by clients to subscribe to events or have the event mutations sent at their respective API endpoint. So now MySQL is actually used as the primary data store for this application. The ACID properties of MySQL makes it ideal for storing the events reliably. Search via MySQL is supported, and the queries are heavily optimized dynamically, but the data store performance is inadequate for certain edge cases. And for this reason, and this reason only, MySQL was used as a backup search data store. So this is how an informed event looks like. So this is the general form of an event schema on your left. It should have an ID, a type, and a start time and an end time for sure. So the type of an event is actually kind of an abstract class, from which the event is actually derived. There are somewhere about 40 types of different event types, like traffic shift is an event, and outage is an event. From a request of deployment of an application to the actual deployment are all different levels of events. All the deployment events actually contribute to major part of the total events generated every day. There are elements associated with every event, like deployment events will have like, let's take an example of a deployment event that will have the application name as an element, the host where it must go, the ID of deployment, and the success or failure of the deployment. The creation of these elements is open to the users of Inform, so there have been more than 150 plus elements in the system as of now. The schema of Informed is heavily normalized. Let's have a look at it. There are few lookup tables. An element lookup table that's contain information about the element's type, whether it's a string, it's a boolean, or it's integer. Different elements have different tables, and yes, they are created dynamically whenever a new element is created by any user. The event table is the main table that contains the event info, and there is a mapping table that maps events with their elements. That this table actually contains the most number of records. So there were multiple inserts across tables for a single event. That is where the transactional properties of MySQL made it a very proper solution for the app. Now the problem. At the time when Inform started facing some problems with native MySQL, there was 0.2 million plus events generated and consumed every day by the application with different PCOS. Each event accounts for almost 10 records across tables. As mentioned earlier as well, there were 40 plus event categories. And while analyzing the problems, the total number of records came out to be nearly 2 billion. And post the ramp up, the expected growth was about 10 to 15x. So all the issues, all the relatable things that I mentioned earlier, they all started to come up one by one. Now the problems. So at LinkedIn, we use MySQL in a multi-tenant fashion. That is, not all MySQL clusters are dedicated for any one application. Many of them have more than one database used by different applications that may or may not be related. They can have different use cases, different thresholds, different requirements altogether. So this database, Informed database, was also hosted on one such cluster with other databases alongside. And this became so write intensive that the load on the primary host normally stayed high, and it started affecting the other databases on the cluster. So hence the name. Inform became a noisy neighbor. They started facing latency issues, connection threshold issues, and whatnot. Typically, all the irritating issues that pile up actually to become the major elephant in the room. So as a solution for the noisy neighbor problem, we moved Inform database to a dedicated cluster of its own, but that was not enough because the heavy transactions on primary started to slowly lag the replicas more often, and they couldn't keep up with the writes. At times, they broke and required to be rebuilt again and again. So this posed a big threat to the availability because we had to keep it as a single node cluster. So next, we vertically scaled the machines. But that wasn't enough either. The latency and slow query issues due to huge data growth still persisted. Now this became a blocker, an issue which is required to be resolved in order to ramp up the application. The only solution that came up after many discussions was sharding. We need to divide the data now. So a one-liner for sharding, it is actually a technique of partitioning a database into smaller, faster, and easily managed data chunks called shards. We found out quite a few solutions to shard the database or either use a solution already present. So first, moving to a different distributed technology was crossed out very quickly as the application was tied to MySQL for the reliability provided by its transactional behavior. The other option was to have application take care of the sharding scheme. using Zookeeper to manage the sharding scheme and Helix for cluster management. This could have been achieved, but just that could have made the application a lot more complicated than it already was. It has to write logic for the scatter gather of data from across the shards as well. So all in all, we just wanted an all-in-one solution that takes care of all of these. And Vitess checked all the boxes for us. So let's know what Vitess actually is. So as mentioned, Vitess is actually a sharding solution to horizontally scale MySQL, completely open source. Other feature which I like the most about Vitess is that it keeps the sharding logic away from the application. The application connects to Vitess just like it is connecting to any other MySQL server. So there were very minimal changes at the application side. The major change was there should be a key present in the table, a column, which we will define as the sharding key, and which Vitess will use it to shard the data across different nodes. Also, the proxy that Vitess provides, also called VTGate, it improves the performance by rewriting the queries that it gets from the application. And managing Vitess is quite simple as one of their components that it provides both a CLI and a GUI solution for the purpose. So a small architectural diagram for Vitess. Let's run through the components here one by one, starting with VTGate, of course. It's a lightweight proxy that routes the traffic to correct VT tablet and returns consolidated results back to the clients. It takes care of the sharding scheme and the required latency as well. In simple language, every select query with a primary key would know which shard to reach, and so every such DML statement with if it has a shard key. Now, VT tablet. A tablet is actually a combination of MySQL process and a VT tablet process on the same machine mostly. It takes queries from the VT gate and also is assigned the type of tablet. So if you want to know what kind of host it is in a cluster, it's a master, it's a read-only, or it's a replica that is assigned to the kind of tablet it has. Now, the central piece, the topology service. It's a distributed locking service, actually. Mostly a consistent data, a key value store is used for it, either Zookeeper or ATCD2. ATCD2 is used by default, and we use the same. It enables, one of their tasks, it enables node discovery for the cluster. And the VT tablets interact with each other using the topology service. It also holds certain configurations which is required by cluster, and those configurations must persist between server restarts. VTCTL and VTCTLD. So VTCTL is a command line tool to administer Vitess, creating or deleting shards, resharding, initiating failovers, etc. VTCTLD is the GUI to perform the same. Now, every time VTCTL or VTCTLD performs any operation, the topology service is modified. There are some more common terms used when we talk about Vitess. vSchema. vSchema is actually the metadata about how tables are stored in Vitess. It is generated as a JSON file with the sharding metadata and the table info. Key space is actually a synonym for schema, also a term for a group of shards for one particular schema. Key space ID is actually the value which is used to decide on which shard the record will live. They can be range-based shards as well, where sharding is done on a range of key space IDs. Okay, Windexes. Now, indexes in Vitess are called Windexes. A primary key or a primary Windex maps the key space ID to the primary key column of the table in vSchema. Every sharded table must have one such Windex defined. Secondary Windexes are also available. They are the additional ones to optimize the where clause. If defined, they will help VTGate direct the where clause in the query to appropriate shards, even if the primary Windex is not given. Right, so that's about Vitess. Now the major part of the process, the migration. So the data was required to migrate it from native MySQL to Vitess. It sounds so simple, right? But it's not so simple when we actually started to face certain challenges. Right, let me go through all of them one by one. So one of the main troubles for the application before migration was that data was too normalized. As we saw the schema diagram earlier, there were parent tables, there were child tables, and the chain even went wrong. But we knew one main requirement of sharding, by Vitess was that every table must have a shard key. So we denormalize the data to some extent. We'll cover that. Query performance, yeah, there was a question. Will it perform the same as the native one? Well, it's MySQL underneath after all. The indexes, second indexes, and primary indexes should work as they work in MySQL. And we benchmarked it with application queries to confirm it. Also, it was our first Vitess setup. So the what if was troubling us as well. What if it didn't work post migration? What if it goes to an unrecoverable state? These were some questions that raised a few eyebrows. The downtime cannot be used. So the migration has to be real time and just a small cutover at the time of switch. So let's say just an application shutdown and application restart. That's all. And migration technique, yes. What do we use to migrate almost a terabyte of data from an unsharded native MySQL to a sharded Vitess? Now, we starting going towards the solutions, now going towards how we did it. And schema migration was the first step because in order to have the database migrate on Vitess from native MySQL, the first step was to tweak the schema. So an initial migration was done by the application team as a one-time activity. After some denormalization, foreign keys were removed across all tables, and all tables were set to be sharded according to their primary keys. But we figured out very early on during migrating a few records that the query to get the details for a single event is actually going on multiple shards. So this was because the shard key was different in all tables. They were all their individual primary keys. So to overcome that, a dummy column called shard key was created in all the lookup tables with a default value. And the sharding was done using this column so that all of those records reside on the same shard. Similarly, an event ID column was created in all of the event element tables for sharding, and the mapping table was also removed. So the schema turned into this. The event ID relationship between event and the element tables was maintained by the application. This resulted schema made the application also shard aware, as all the records related to an event resided on the same shard. Yeah, I'll let that sink in. Okay, moving on. The migration technique. Yeah, this was also one of the major challenge because we figured out a few migration techniques that could be carried out to migrate the database to Vitess. vReplication is a component of Vitess for the same purpose, but we couldn't leverage it as it was in the development phase at that time when we wanted to migrate the data. The other approach was dual writes by the application, that the application could write to both native MySQL and Vitess simultaneously. But again, that could have increased the complexity of the application. And at that scale, even a small failure of writing in either of the targets would have led to hours of debugging. So we went ahead with a custom approach that I'll be explaining here. So Prework. We had a staging database setup for the application, which was used by them for testing and UATs. So we experimented the migration technique on that to first create a staging Vitess cluster and benchmarked using the application queries. We had a native one primary to replica setup initially working on row-based replication. We converted that native cluster to a statement-based because we wanted to use the binary logs over VT gates. And VT gates do not understand the row events. It will understand SQL statements. So now starting, we stopped the replication on one of the replicas, took a complete dump from it, restored it on one of the VT gates, and it sharded that across the number of shards. In staging case, we had 2 shards. Then we replayed the binary logs post the backup position from that same native replica to the VT gate. And we had written an application for that. Then we started the replication on native replica so that it is in sync with the latest data on the native cluster. At the time of cutover, when the application writes stopped, we made the native primary as a read-only host. So when restarted, the application started pointing to VT gates and it started writing to Vitess. Only the initial sync, the sync between taking a dump and then the replication was restarted, that sync took time. but when the setup was in sync, there was no lag at all, and the data was being migrated real time. On the day of cutover, we restarted the application to connect to Vitess, which only took like 5 to 10 minutes. So we migrated the staging cluster, and the total downtime was 10 minutes, which included starting and stopping the application. Also, the data was actually got migrated real time after one sync. And at the time of denormalization, there were 2 billion records in total, which got increased to 4 billion plus when we started the actual migration. Right. So we had some observations post some benchmarking done on the staging Vitess cluster. The full table count queries of even bigger tables, as big as 200 million records, were getting the results 3 times faster than the native MySQL setup because of small chunks of data sharded across. Also, the primary key lookup was faster. There was latency in the queries until the shard key was not common in all the tables after daemon or normalization. We already discussed that we added a common key to shard, and that improved the performance a lot. The write latency was as good as native MySQL. We noticed some resource consumption during big scatter gather calls on VT gates and vertically scaled them a little. Uh, the joins worked as they work on native MySQL if the key space is common. We also tweaked a lot of SQLs that took a lot of time, like adding the event ID wherever we can to the where clause to improve the queries. And Windexes were created on the tables and defined in the V schema to reduce the additional latency of the scatter gather queries on VT gates. The outcome is this. So this is how the Vitess powered infrastructure looks like. Uh, we have a 4 shard Vitess cluster. Every shard has 3 MySQL instances, 1 primary and 2 replicas. etcd is present on every node as a distributed topology service, and there are 4 VT gates for availability, which are used by the application. So in the top left corner, if you notice, that is the migration pre-work we did in the last some slides, and did the same for prod setup as well. Orchestrator was plugged in for high availability. VTCD is used for the GUI or for Vitess administration. And on the top right-hand side is a single shard cluster that we use for auto increments, because Vitess didn't support auto increment feature of MySQL, but it does gives an alternative. So the sequence schema, somewhat like, let's say, Oracle sequences, provides the next ID to the tables we assign it to. We need to have one table in the sequence schema for every other table that requires an auto increment. So let's say if we have 150 plus tables, 150 tables, we need 150 sequence tables in the sequence schema, and the metadata should also contain them. Right, so this was the main setup and we did well, but one question remained unanswered still: what if? Which we had to keep in mind. So we created a rollback cluster for the setup. We leveraged MySQL's multi-source replication capability and created our rollback plan. Using 1 replica each from the 4 shards as 4 primaries, we replicated the data into 1 native MySQL node using multi-source replication. That node also has a replica of its own. Though we are now much more confident enough that we might not need it, and the setup is running successfully for almost an year now, but what if? So that concludes the migration part. Let's move on to the impact. What impact Vitess had on the application? For all the queries that were served by a native MySQL cluster and are now on Vitess, 96.5% of them are returning under 100 milliseconds. The total data fetched from the queries lie around 15 to 20 MBs. Over 500,000 events are created every day on the platform and are immediately searchable through Vitess. And as mentioned in the beginning, the native MySQL cluster was largely affected by writes and couldn't keep up with scale. That affected the availability of the application as well. If MySQL goes down, the application goes down. Post Vitess migration, the application now serves at 4.5 nines of availability with no CPU spikes or loaded database clusters. Right, so with that, we are nearing the end of the session. So I'll just reiterate a few points and add 1 or 2 new ones as well. We couldn't agree more that Vitess came out to be a clear winner for us when we were looking for sharding solutions. One small thing to note, that application also uses Elasticsearch for a few features, but the latency search search latency of results, which is provided by Vitess, is actually comparable to it. Also, for us, Vitess became the major data store for the application, as it serves 131 times more number of queries than Elasticsearch serves. The migration was completely online, real time, after initial sync, and the downtime was kept minimal. And we have a clear rollback plan in case the application requirements change down the line to not use Vitess or the what if. With one such setup, we are now onboarding a couple of more internal use cases to Vitess, and additionally are also working on tooling around Vitess so that we can have a fully managed Vitess at LinkedIn. Thank you. Thank you very much. We can take questions now. All right. How long did the move to Vitess take your team? How long means how long it took our team to move to Vitess? Yeah, it took some time because we did some kind of POC and the requirement gathering of it with the clients. So yeah, it took around, I think, near about 6-7 months to completely migrate them. And yeah, fully managed Vitess, maybe talking about if clients want, they can spawn the clusters automatically and how many shards they want, if they want to increase or decrease in the number of shards. Yes, we are running VT tablets on the same machine as the corresponding MySQL instance. There was some resource consumption, but I think a one-time calculated scale should be fine. No, as such, they are not running in containers, but we might down the line have a plan to move them to containers.